In this video, we're going to illustrate how carriers move around in BJTs, which will give us a qualitative sense of how transistors achieve the magic of transferring electrical signals from one terminal to another. If you look at a BJT, your first instinct might be to model it as two back-to-back diodes. After all, there are two PN junctions that make up a BJT, so one here and one here. I'd like you to take a minute to write down any details you notice about BJTs that make it different than two back-to-back diodes. Okay, first it's worth noting that the doping is different on the left PN plus junction and the right PN junction. That means the two diodes we include in this model would need to have slightly different IS and V-on values, which we call VBE-on and IES for the base emitter junction, and VCE-on and ICS for the base collector junction. But that seems like a reasonable modification that makes the back-to-back diode model better and not worse. The more interesting detail that this model overlooks is the very thin base region. That suggests the two diodes might be able to interact, and we'll see that's the case under specific bias conditions. The first bias condition we're going to examine is one in which both PN junctions are either unbiased or reverse biased. As you might expect, that means little current flows in either PN junction. We call this bias condition cutoff, and we model it with two open circuits in both the large and the small signal regime. Notice, by the way, that we're super zoomed in on the base in this picture, because most of the exciting behavior in BJTs happens in the base. The second bias condition we're going to examine is one in which both the base emitter and the base collector junctions are forward biased. I've indicated that in the diagram with external voltage sources down here attached between the base and the other terminals. This results in current flowing out of the base into both the emitter and the collector, just like two forward bias diodes. This bias condition is called saturation, and we model it with two voltage sources in the large signal region. In the large signal model over here, which is still just like the back-to-back diode model. Notice that we've used different notation in our diode description over here for electron flows and hole flows. And notice also that this notation includes weighting, showing that there are many more electrons flowing on the N plus P junction than on the NP junction. The size of a carrier flow is proportional to the doping of the region injecting carriers, so the N plus region injects the lion's share of carriers in the base emitter junction, and I've used a double arrow to show that. The next bias condition we're going to look at is one where the base emitter junction is forward biased while the base collector junction is reverse biased. You can see that the base collector bias has reversed direction down here, which will mean that the collector is at a higher voltage than the base, and the base is at a higher voltage than the emitter, at least as drawn. The emitter side of this BJT works like a normal diode. Holes are injected from the base to the emitter, and many more electrons are injected from the heavily doped emitter into the base. Because the junction is forward biased, these carriers are primarily driven by diffusion, which I've noted down here. The collector side is reverse biased, so any electrons that stumble into this depletion region will drift to the collector. Note that this creates a current traveling from left to right, so this way, because electrons are negative charge carriers. Note also that this drift behavior is relatively insensitive to VBC. As long as the junction stays reverse biased, then this carrier flow will be dominated by drift. These two carrier flows mean that the concentration of electrons is going to be very different at the emitter junction, where many electrons are being injected, and the collector, where they're being swept away by drift. That means there will be a gradient of electron concentration, or minority charge concentration, across the base, which results in diffusion from the emitter to the collector. So electrons diffuse from the emitter side to the collector side. That's captured in this arrow. Put another way, the base emitter diode injects a lot of electrons into the base, but many of those electrons get stolen by the collector instead of being cancelled by holes in the base. However, not all the minority carriers injected into the base make it to the collector. Some balance the small hole current that's coming out of the base, and some just recombine with majority carriers on their transit across the base. Canceling out those two effects are why the doping profile in BJTs is so important, and why the base has to be thin. A thin base means that the electron transit time is short, and there's relatively little opportunity to recombine. And a very asymmetric doping profile means this hole current is much smaller than the injected electron current. We describe how effective a BJT is at getting the electrons from the emitter over to the collector using a parameter called alpha, which is the ratio of IC to IE. It's also the ratio of electrons that come from the BE junction to the CE junction. Those two things are the same. In well-designed BJTs, alpha is often close to 99.7%. These complicated effects can be summarized with this large signal model, where the emitter current is determined by the base emitter voltage, so across this diode. But most of the current that flows to the emitter is provided by this dependent voltage source between the collector and the base. So this captures the electrons being injected from the base emitter junction and then swept over to the collector. The portion of current that's drawn from the base is 1 minus alpha times IE, because alpha times EE is provided by the collector. Notice that current runs from the collector to the emitter in this model because electrons are flowing in the opposite direction from the emitter to the collector. And notice also that the emitter emits electrons in an NPN device. In general, it emits minority carriers in the base. But that means that in NPN devices, the emitter emits electrons and sinks currents. Students have gotten tripped up on the name emitter before, and it's worth taking a minute to remember that. So in summary, BJTs look like back-to-back diodes, but that's not the whole story of how they operate. In cutoff, which is when VBE is less than VBE on and VBC is less than VBC on, we have no current in a BJT. In saturation, where VBE is greater than VBE on and VBC is greater than VBC on, we have diode current from the base to the emitter and from the base to the collector, so that usually just looks like voltage sources in our switch voltage source model. And in forward active, where VBE is greater than VBE on, but VBC is less than VBC on, we have diode current from the base to the emitter, but a large fraction of the injected electrons from the base emitter junction reach the collector instead of being cancelled by holes from the base.